My name is Mihail. I'm a senior data scientist at GetYourGuide.
And I'm Theo, a data science manager at GetYourGuide.
And today we'll talk about how our team adopted deep learning for ranking activities in our marketplace. So for the agenda today, I'll start off by giving a little bit of background about GetYourGuide, like who we are, and why ranking plays such an important part in our marketplace. Then I'll briefly introduce the learning to rank framework and how it can be used to build machine learning models for recommender and ranking systems. After which, Theo will talk about the state of our ranking system roughly about a year ago when we embarked on this journey towards deep learning and sort of what motivated us to do so. And then, as well as how we kind of approach this migration when it comes to experimentation and what were the kind of challenges and learnings that we faced along the way. And in the end, I think we should have plenty of time for questions, so we're hoping for some engagement from you as well. And we'll just wrap up with an overview of the model that we ended up with, as well as the key takeaways. So for those of you who are not familiar with GetYourGuide, we are actually the leading marketplace for discovering and booking activities online. So we operate as a two-sided marketplace, which means we have two types of users. On one hand, we have the suppliers of the activity, so think someone like a museum or a walking tour operator who wants to join our platform to list their activity online. And then on the other side, we have the travelers, who are people who are planning their next trip and want to find things to do there. And ranking essentially plays a very important part in matching the activities to the travelers, right? So whenever users come to our platform and query our marketplace, the first step for us is to retrieve the set of activities out of all possible activities that we have online that could be relevant to the user. So we use pretty loose matching here. So is the activity tagged to the location that the user is interested in? And after we do this retrieval, the second step is to actually rank those activities in order of relevance for that user. And yeah, as we know, screen sizes and user attention can be pretty limited. So this really just means that inherently the top positions that we display are much more valuable in some sense to the user. So really optimizing the ranking of the displayed activities for us can go a really long way to help the user actually discover and see what they are interested in and essentially maximize their chances of converting. There's many factors to consider, which makes this a rather complex task. Things like the seasonal patterns of the location. You know, is it in Europe or somewhere in the Americas, for example, can have different patterns, different user constraints like the language that they're interested in, the historical performance of the activity, and even the user's own unique interests. So everyone is interested in different things, everyone's unique. So for example, here, the landing page of Barcelona could look very different for two users if one is interested in more kind of culture and museums, let's say, or architecture, and the other user is interested in more outdoor activities. Both of these are very valid for the landing page of Barcelona. So how do we go about this then? The learning to rank framework has really kind of emerged really for the better part of the 2 decades now as the sort of de facto framework for solving this task. And it essentially boils down to using implicit user feedback from their historical user queries. So as they search our platform, our marketplace, to kind of determine what is relevant for them, and then use that data to train a new machine learning model and kind of use it to serve new rankings. So as users come to GetYourGuide and interact with our marketplace, they essentially submit a search query, maybe some filters to go along with that query. And we then, in return, return a list of activities to display to them. A ranked set of activities, I should say. And this happens with like millions of users every day. And as that happens, they also interact with different activities shown to them. So for example, clicking, viewing, and maybe even booking something, which generates event logs for us. And then what we can do in turn is, under this learning to rank framework, using those event logs, we can process those events and essentially train a machine learning model on that data. So using the clicks and bookings, we can kind of then retroactively determine what was relevant and then train a new model on that. So kind of closing the loop. And then we evaluate the model. If it looks good, we publish it to our model registry to be then available to the ranking service and kind of serve new rankings, updated, better rankings. So this is done every day. And at this point, I'll hand it over to Theo to give a bit more details on this part. So what exactly was our machine learning modeling stack and why we decided to move to deep learning.
Hi. Yeah, so now I want to dive in a bit more into the ML model, which is this part on red. And what we get basically from the user is the query, and after it was preprocessed, we have the query and the activities, and then we need to combine them. So first, we will get also information about the activity features from an in-memory database, and we also get information from the traveler history thanks to our feature store. And when we have all this information, we can combine them, and they are passed to our scikit-learn pipeline. The first step will be to preprocess them, and for that we use some scikit-learn transformer with doing operation on pandas data frame. And the second part is to do the predictor with this XGBoost. And what we used until moving, what we had around 1 year ago was this XGBoost ranker following the learning to rank that Mihail just explained before. And what we want to focus on and change is this XGBoost ranker and moving it to a deep learning with PyTorch. Okay. But maybe you will ask why do we want to move to deep learning? First, we saw that we had a diminishing return with our tree-based approach. So we felt that we were kind of reaching the limits of what was possible with XGBoost. Second, on the other hand, we saw that deep learning offers a lot of flexibility, in particular in terms of model architecture and also being able to customize the loss. We are also know that deep learning will be able to exploit a much bigger data set. And finally, we will be much freer to use more features, like especially the one that have a high cardinality for categorical features, also being able to fuse different features like text, images, etc. And finally, and maybe the most important, we also had external validation from industry case studies. So we saw that other marketplaces like Airbnb, Wayfair, Etsy also moved at some point their ranking from a tree-based to deep learning, and they all claimed that it was transformative. So based on that, we saw that we'll just use deep learning and throw GPU at it, but it was a bit more complicated than that. So a bit more seriously, by looking at the other companies, they also share a bit their journey, and also we talk with some people. We knew that we would expect like a long and complex process, and for some time without a business win. And indeed, yes, that took us 6 months to get to the first stage. Then we also know that going to this deep learning will probably go with some infrastructure investment. In particular, we expected to have a larger training time. And yes, that really is a problem. And actually, we had to reconfigure a bit our continuous integration to be able to handle that. Then we also expected to maybe have problems with GPUs. Actually, it was easy to train on GPU. However, training on multiple GPUs was a bit trickier, especially there are some weird things happening with embeddings and the max norm in there. That took us quite some time to figure out. And finally, the inference latency thought that maybe it will be a blocker for us. And we also needed to tweak the Torch CPU threads setting, and also we are seeing also some weird things happening now with the memory usage and latency that play some interesting role. But what we were the most afraid actually was what is not shared in the blog post. So what will be the unexpected thing for us? And actually, we got one, the Docker size, the Docker image. When we added PyTorch, at first we just like exploded the Docker image by getting more than 4 GB, which causes some problem to our continuous integration pipeline that was running out of memory. But we figure out a way around. So yeah, that's the thing and what we were expecting and what really happened. Now I will show you a bit more how we broke down this deep learning to major milestones. And how we did that basically is first in Q2 last year, we decided to focus on getting the technical parity between the tree and the deep learning models. In particular, I mean like just being able to handle the throughputs and the latency requirement of our model. And for that, we started with a minimal hackable network. We spent the whole full team working 2 focus days, trying to pairing together to get that happening. And we just got with that with a very narrow network that was just trained on 4 features instead of the 50 that we are using for a tree-based model. And we were able to deploy it behind a feature toggle to be able to do internal testing. With this, we were able to start planning and preparing our second iteration, minimal variable network. So basically, we were using a very simple architecture, but we were able to use all the features. However, it was just okay on our ranking metrics, but it was still not optimized for all our business goals. But we still wanted to launch an A/B test and to get some learning of it. So for the one who are not familiar, A/B test is basically we diverted 50% of our traffic to have the activities ranked by this new model instead of the tree-based model. So we have some real data of what will happen with this new deep learning model. And so we were able to validate that throughput and latency were there, but we still had the last step that was still not there. That's why we launched this minimal lovable network where we also were able to achieve all the business objectives. So we had the same business objective as the tree-based, and also we had ranking metrics that was better, and that's how we concluded the first step of the first milestone for Q2. Yay, we were happy. Then in Q3, we continue and say, okay, now we are trying to move towards a business parity, meaning that we want to have the same business performance as the tree-based approach. And so for that, we started experimenting with new architecture, and what we saw is changing with a transformer architecture with using self-attention help us. And we see big improvement in our ranking metrics, and we were pretty excited to test it in an A/B test. But that we saw is actually we had more people bouncing on our website, meaning we had more people on the B side when they saw the new ranking, just look at the page, but did not click on anything and just came back, closed our page. So with this learning, we say, okay, we need to go to something else, and we introduced the clickbait transformer, where we reuse the same architecture, but then we increase the data set to also add data of visitor who clicked on activity and not just booked activities. And then we saw a flat business result, and more specifically, we also saw that we removed this problem of increase of bouncing. So that's where we achieved our second milestone of business parity. And now we said, okay, we're ready. Now we can get better, right? We want to go to deep learning because we want to have a better ranking. And actually, in Q4, That was the goal, and it took us still quite a few experiments. So 4 experiments later, without a business win, we finally got our first win. So here what we did is, on top of all the things that I explained before on the transformer and the data set improvement, we added the semantic similarity between the activity that we have and the category of the page. Thing for us, the category of the page can be like the wine tasting in France, where will be a category, or like monk meditation in Japan. All of those are categories for us. And we saw some uplift actually in the ranking metrics, but more importantly, we saw a significant uplift in the number of bookings. And yeah, that was just before Christmas. It was a perfect Christmas gift for us. And then in Q1 this year, we had our biggest win from the last year with the latest model. So here we started to go much deeper into the architecture and introduce a deep and cross neural network, also with added trainable embedding for our categorical features. And we also increased the size of the data set. And we saw a clear win in our ranking metrics, and the booking and revenue were also significantly positive in our A/B test. Okay, with that, I will give it back to Mihail, who will show you a bit more the current architecture.
Cool, thanks. So maybe at this point, some of you might be wondering, okay, so what does it actually look like? What is the model that you ended up with in the end? And well, here it is. I can run you through it quickly. So basically, our ranking model that we ended up with at the end, as Theo just explained, is this deep and cross architecture, but it actually consists of 2 main components. So the first one being the deep and cross network that's shown here. And then on top of that, we have the ranking transformer at the very top of this graph. And it all starts with the embedding layer. So the task of the embedding layer is essentially to take your sparse features and create dense representations for them. And in our case, a sparse feature could be a simple categorical variable like the language that the user selected, or even a specific entity, so the activity ID or the location ID that the ranking request contains. So we're training embeddings on the entities themselves, the entities being ranked. After that, we actually concatenate the embeddings that are generated by the embedding layer with other dense features. So this would be like the historical performance of an activity. And then there's 2 parallel kind of sub-networks here. The left one shown, highlighted here, is the deep network, which is your kind of standard fully connected network with some non-linearities in between. So in this case, we're using a ReLU activation. And the task of this deep network is to essentially generate kind of highly nonlinear and highly dimensional features out of just generate the features. And then on the parallel to that, we have the cross network, which actually applies linear feature crossings to the inputs. So a feature crossing would be something like the example shown here, which is a 2nd degree feature crossing. It's a simple AND statement. So if the category of the tour is brewery tour, or activity rather, if the category of the activity is brewery tour, and the language that the user has selected is German, maybe that activity should be ranked higher. So this kind of explicit linear feature crossing is something that the cross network can do very effectively, but on the other hand, traditionally, deep networks with non-linearities kind of struggle with this kind of representation. So after that all is done, we actually concatenate the 2 outputs of those networks, the 2 sub-networks, and feed it further to the ranking transformer. So this is, of course, for those familiar with the Attention is All You Need paper, it's inspired by that. And this network actually consists of 2 encoder blocks highlighted here. So each encoder block has a 3-headed self-attention, followed by a feed-forward network with some skip connections and layer norms in between. And after that is done, there's the final kind of just linear layer that gives us the relevance score. So then, based on that score, we actually rank the contents of a specific ranking request. And the task of this transformer is essentially to kind of look at the contents of the ranking request, the query, so the different activities contained in a single request, in a more holistic way, so kind of modeling the entirety of the query. So at this point, I'll hand it over back to Theo to give you some of the key takeaways that we had.
Yes, thank you. So yes, I think from this journey, we had 3 takeaways. The first one is actually start simple. So we actually reuse as much as possible from the XGBoost model from the start. That means that we reuse the same data set, the same pre-processing using the scikit-learn pipeline, and then we incrementally we incrementally test the changes, first offline and then online. And so in that, that's how we end up testing more than 50 iterations and launched 10 A/B tests in the 6 months. And that's actually allow us to learn quickly and readjust all the things. Like one good example is the people bouncing. It's not something we could only learn through A/B test. Then the second one that I think was very key for this project was to split the project in different milestones. So here we break it in 3 milestones. The first one was just to get the model to have the technical parity, then business parity, and finally get business improvements. So that allows us to celebrate the achievements and also help to show the progress that we have to our different stakeholders. And finally, stay agile and be ready to expect the unexpected. You can prepare and learn from others, but be ready for some bumps in the road. This is a big migration, and there will be some surprise on the way. Great. With that will be the end of the talk. I just want to say thank you, and in particular to all the people. So there was a full team working, and in particular like Nikhil, our PM, Jui, also a data scientist, and Olivia and Xingting, our MLOps engineer, that's made it possible. So yeah, thank you, and looking forward to your questions.
Thank you.
Okay, thank you too for the presentation. We have a lot of questions from the audience. So the first question is, since you update your model daily, have you ever investigated or experienced cyclic model retraining behavior due to the day of the week effect, for example?
Sorry, what was it? What kind of behavior was it?
Cyclic behavior in the model retraining.
Okay. Yeah, for sure. So for sure, as I mentioned, there's like seasonal patterns that we need to kind of be aware of, and this also includes shorter kind of terms. So within the week, what day of the week? Typically on weekends, for example, we see a lot more traffic at different times of day, and etc. So that is something that we need to be aware of and take into consideration. So it could be as simple as adding the day of the week as a categorical feature and maybe creating an embedding out of that. So that would be like the way we would go about it.
So how did you realize or quantify that you were reaching the limits of XGBoost as a method?
Again, yeah. I mean, basically, we were still experimenting on our tree-based approach, and what we were saying is like getting the next wins was getting harder every time to get a successful A/B test. So we had a few iterations of experiment where we saw like, okay, like we see that offline we don't see as much uplift that we hope to get to a significant result, and also we also get to the point of we think that the next step will be to do that, but actually it's not part of the framework, and we'll have to hack things around in different way to be able to make that happen, or actually it come naturally when you go to deep learning. Like for example, we had problem with like high cardinality categorical feature, which if you want to do it tree-based, it's just like hot encoding. But when you have a 1,000 cardinalities, like you have a very huge vector which have a lot of problems in terms of latency and also just like I'm missing the word. Throughput. Yeah, the performance of the model. Yeah. Yeah,
and I would say, like, besides just the kind of diminishing returns that we saw in terms of like model performance and A/B testing, I think we really like the flexibility of PyTorch as a framework. So it really allows you to kind of have a lot of flexibility in how you configure your model. You can easily set like custom losses in pretty much. You have a lot of freedom to do things there. So those things are not so straightforward with our previous framework. So that was another big reason.
Mm-hmm. So another question that interests a lot of people is which metrics were used to evaluate your rankers?
Yeah, that's a good question. So
I would prepare it, actually. Let me go to...
Yeah, so I would say, so there's a lot of different metrics, actually, that one can look at when measuring relevance. I think there's a ton, really. And I think, so here's like an example of how you would go about it. And this is probably the most straightforward metric. It's called the average precision. So essentially, you need to first declare what is relevant as a binary label, 0 or 1. So in our case, it could be the activities that the user clicked or booked, as shown by the two different colors or highlighted by the yellow and orange. And then you go position by position. So this sum k, which signifies the position, you kind of average the precision up to that position, and then you take the total average as the kind of one ranking metric. So yeah, I mean, the point is to like essentially, or the goal of this whole thing is to like rank the most relevant things, which again is under the learning to rank framework is just used or determined by user logs, so the clicks and bookings, and then take those and try to rank them as high as possible and then serve that model. So here's one example. There's other metrics like NDCG, very common also in the literature, but
we looked at a lot of metrics. This map is actually the one that showed the biggest differences. Like, for example, the NDCG, we don't see as much delta between different ranking, whereas the map was actually the most relevant one. So, but actually we looked at a lot on like by categories, the price of the top activities, etc.
Yeah, it's very specific to the problem and the data as well. So what works for us might not work for everyone else either.
So we still have time for one last question for 1 minute. How did you handle the latency of transformers? So was it an issue in the beginning, and how did you try faster implementations?
Do you want to take this?
Yeah, I think the transformer in itself was not a major problem in latency. The overall architecture with the dip and cross actually is taking a bit more time, but it's more the introduction of the dip and cross that causes some latency issue. But the transformer in itself was pretty efficient, so we didn't have to do a specific thing to make it work.
And I think there's a lot of trial and error. We have some very good MLOps engineers who come up with like some really clever tricks to help there. So I think there's no like one solution or one answer for everyone, but I think it came down to like a lot of trial and error and make the improvements that way.
So thank you for the presentation and also for answering the questions. We were unfortunately not able to answer all the questions, but maybe you can come to the front, or I can send you the questions and you can answer them on Discord. So thank you again for the talk.
Thank you.
Thank you.